Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior astronomer at the SETI Institute and chief scientific officer at Unistellar. Today, we are going to talk about volcanoes, but not any type of volcanoes. We're going to talk about volcanoes and how we could detect volcanic activity on exoplanets. And for this, I invited Colby Ostberg. Hi, Colby. How are you?
Good. How you doing, Frank?
So Colby is an astronomer at UC Riverside, and is the lead author of a very interesting study on basically the detection of terrestrial exoplanet atmosphere, and he's been published in which journal? I'm sorry, I forgot.
It's okay. It's the Astronomical Journal.
Astronomical Journal, and is entitled "The Prospect of Detecting Volcanic Signatures on an Exo-Earth Using Direct Imaging." Okay, so let's dig into this topic, Colby, because that's a very interesting topic for our audience. I'm just going to mention that I did my PhD on the study of volcanic activity on Io. So I am also very biased to our volcanoes. When I saw this paper, I say we have to invite Colby to talk today about that. Okay, so what is the question you were trying to answer with this research, and how did you do it?
Yeah. So basically, as the title states, and as you mentioned, the goal was to first just determine what would volcanism on an exoplanet look like. And so there's different methods that we use to determine what's going on an exoplanet. And so one of them is direct imaging. And with that, basically we can block out the light from a star and just look at the planet that's orbiting it. And so with that, we can determine what sort of composition the planet atmosphere may have. And so we wanted to see whether, if there was large-scale volcanism happening on an exoplanet, what kind of things could we see in its atmosphere that would tell us there was volcanism happening. And
Okay.
yeah.
So you started with an hypothesis. We know there is exoplanets in our galaxy around stars. Each star has an average 2 exoplanets, and there is a lot of terrestrial planets. So now let's assume that we have built an instrument capable of imaging those exoplanets, space telescope. We're going to go back to that.
Mhm.
And there is this volcanic activity over there. What will be basically the signature or the indication that there is volcanoes on the active volcano on this exoplanet?
Yeah. So I guess that's kind of getting at the results of our paper. And there's a couple things that we determined would be the best identifiers for volcanism occurring on an exoplanet. And for one, when the output from an eruption goes up into the atmosphere, chemical. Sorry, you're like at an airport. That's crazy. When the sulfur dioxide is pumped into the atmosphere after an eruption, it can chemically react with ozone in the atmosphere, especially we see that here on Earth. And that chemical reaction will slowly remove large abundances of ozone from the atmosphere. And when we look at the atmosphere of an exoplanet, we can see that ozone is absorbing light, and we can detect that there is ozone in that atmosphere. And the way we do that is we basically see a feature, I guess I could say, in the atmosphere. And the size of that feature will be based on how much ozone is in the atmosphere. And so let's say you look at the exoplanet before any eruption happens, you will see that there is a certain amount of ozone, and it'll leave a certain feature of a certain size as well. And after the eruptions start, the product from the eruption will slowly eat away at the ozone, and we'll see the ozone feature decrease in size. So we can see that there is a fluctuation of ozone abundance occurring in the atmosphere of that planet. And on Earth, ozone is relatively stable. And so if you're seeing large scale changes in the abundance of ozone, you know that there's something significant happening. And we didn't look too much into whether other things could mimic this large change in ozone, like other large scale events, but it is a really strong signature of volcanism, is detecting changes in ozone. And there's other things too that we noticed. Same thing with water. The eruptions that we modeled pumped a lot of water into the upper atmosphere. And so from that, again, we can see changes in the abundance of water in that atmosphere over time. And so that's another thing that we could potentially look for. But in general, I would say that it's not something that a single observation would be able to confirm. It's something that would have to be a campaign of observations where you're noticing these changes in these abundances over time.
Okay. So before we dig into more the details of this study, I just want to say hello to people joining us from Manchester, UK, from Georgia, USA, from Monifil, Scotland,
Oh, cool.
from Jersey, from Chesterstack, but I don't think that's a place. That's probably a name of someone we know. From Woodlands, Texas, from Montenegro in Europe, for Cornish Flat in New Hampshire, from Iraq, from Wiltshire in UK, South Bend, Indiana, and so on. So welcome. You are watching a SETI Live. Today we have Colby telling us how we can detect volcanic activity on exoplanets using different facility capable of imaging exoplanets. So concretely speaking, you described kind of the result. You did this through a simulation. Can you tell us a bit, guide us through the work you did, the simulation, the tool you use, and what exactly you simulated?
Yeah. So all this work occurred while I was doing an internship at NASA Goddard in Maryland. And so there's basically like two different types of models that we were using. And for the first step, the person that was my advisor while I was there on my internship and helped me out with the paper, Dr. Scott Guzevich, he ran a global climate model called GEOS. And these models are pretty insane, state of the art kind of stuff. And with these models, you can basically model the chemical reactions that occur in a planet, how the climate will change when you change the chemical components of the atmosphere. And you can run these for however many years that you want. And so that was what Dr. Scott Guzevich did. And I basically took his data from this global climate model and plugged that into a online interface, which everyone could go check out if they wanted to. It is called the Planetary Spectrum Generator. And I took that data and basically assumed that the Earth that we were modeling was an exoplanet. And with the Planetary Spectrum Generator, you can generate or estimate what that planet would look like or what its atmosphere would look like if it were an exoplanet. I didn't go into too much detail about like what kinds of eruptions. So if you want me to talk about that stuff too, I can.
Okay, so you simulated eruptions. I mean, what type of eruption did you simulate? I mean, did you use some baseline from Earth? So how did you do the simulation?
Yeah, thanks for asking that, because I wanted to mention that. So these aren't just like the eruptions that we're modeling are huge, like some of the biggest that have occurred in Earth's history kind of eruptions. And they are technically called large igneous province eruptions. And so these are just like massive areas that are pumping up magma and pumping volcanic gases up into the atmosphere. And like one of the famous ones you can look up, I think it's called the Siberian Traps. And just the scale of these is way beyond some of the eruptions that we see today.
Mm-hmm.
And so we modeled different kinds of eruptions to see whether like the different amount of volcanic gas that's pumped out makes a different signature or changes whether that signature would be detectable. And the size of those were scaled based on like the amount of sulfur dioxide that was pumped into the atmosphere, and it ranges from 2 gigatons to 60 gigatons. And for scale, I believe like the average sulfur dioxide output of all the volcanoes on Earth per year is around, I think, like 0.1 gigatons or something. It's much smaller than the eruption.
0.01.
Yeah.
0.01. I look at this in your paper, in fact. So
thank you. Yeah.
Yeah. So you simulated eruption, like extreme eruption, but eruption that we had on Earth. I'm sorry, there is airplane flying above me because it's Fleet Week in San Francisco. That's
perfect.
The reason.
Yeah.
I did not plan it will be that loud. Anyway,
it's okay.
So okay, so we have this eruption. They last for how long? 4 years? 5 years?
Yeah. So for each of we did 4 different size eruptions. We had them erupt every 3 months for 4 years. So that'd be like a total of 12 eruptions. And so as they're pushing things in, or pushing these volcanic gases into the atmosphere, the model is constantly determining how these gases would interact with the gases that are already in the atmosphere, the changes to the ozone, all of this. And so after the 4th year, we stopped the eruptions, and then we kind of just let the atmosphere chill out and see what happens naturally to these gases and haze that are pumped into the atmosphere. And as I mentioned, the volcanic gases will eat away at the ozone and decrease the amount of O3, which is ozone, in the atmosphere. And the haze that is produced will also block a lot of the light that would get reflected back if we were to look at Earth as an exoplanet. And so for the first 4 years, we see a decrease in ozone, we see the haze there. And then after, for the last 4 years of the simulation, when there's no more eruptions occurring, we see the ozone begin to be replenished. So the abundance of ozone is increasing in the last 4 years, and we see the haze start to basically fade away. And yeah, sorry, hopefully that answers your question.
Yeah, what is important for our viewers to understand is that those models are very complex. I mean, they take into account the combination of the amount of energy coming to the stars, how this energy interact with chemically with the molecules in the atmosphere, forming haze, which are kind of dusty particles, basically hiding part of the surface of the planet. I mean, it's not an easy task. That's why it took us years to develop those kind of model, the CGM model that you mentioned. Those models are extremely complex, and they are used a lot now to predict as well climate change and on Earth and so on. Yep. Okay, so I hear an airplane coming. So quickly, what can you learn from this kind of detection? Like, let's assume we give you a spectrum or multiple spectrum of an exoplanet, terrestrial exoplanet. What is the key feature that will tell you that there is a volcanic activity?
Gotcha. And thank you for clarifying the complexity stuff. The stuff is pretty wild what we can do with these models. So it really depends what we can see in these spectra in regards to identifying volcanism. But for this specific case that we're talking about, where it's an exact exo-Earth, has the same atmospheric composition as Earth, the main things that we would look for are what I mentioned before, with the changes in the ozone and the changes in the water features as well. But what would be ideal is just detecting sulfur dioxide in the atmosphere. But the problem is that, for one, we wouldn't be able to see the sulfur dioxide absorption because the ozone absorption is much stronger. And so basically the ozone is preventing us from seeing any sort of sulfur dioxide absorption. And that sucks because sulfur dioxide would be a pretty clear indicator in one observation. You wouldn't require a lot to tell that there is ongoing volcanism. And the main reason for that is because sulfur dioxide has a very short lifetime in the atmosphere of Earth, where if you have a volcanic eruption, the sulfur dioxide from that eruption will be quickly dissipated away via chemical reactions or ionization from high energy particles from the sun. And so because of that, if we see SO2, sulfur dioxide, in an atmosphere, either we're really lucky, which is very unlikely, or there's something that is continuously pumping it into the atmosphere to allow it to be, for us to detect it.
Okay.
So SO2, sulfur dioxide, would be the best indicator for that.
Now, let me say that we have people joining us from Austin. Hi, Michael. From Germany, from San Francisco, from Toronto, more people from Germany, from Barcelona in Spain, Catalonia, and so on. So we are talking about exoplanets and specifically exoplanets with active volcanic activity. So we cannot detect SO2 because it will be very difficult to dissociate very quickly in the atmosphere. But ozone is truly a marker, and that's one of the main results of your paper, right? Is that at the end, the way we can be not certain but confident that there is a volcanic activity on the planet is by looking at the ozone absorption line. Did I understand that properly?
I would say that is probably the best chance that we would have. And, you know, if you, for those of you, if you go and look at the paper, you'll see some plots, and hopefully they're somewhat understandable. But the things that I show are very ideal. And in reality, you know, if we want to, let's say, look at a planet today, we detect ozone, and then we look at the planet again in a year, and we see that there is a difference in ozone. Things just, in theory, that sounds great, but in reality, things aren't that certain. When we get data from these exoplanets, there tends to be a good amount of uncertainty naturally, just because, you know, we're looking at a very tiny planet from very far away. There's uncertainty in the data that we get, and so the ozone would likely be the best chance, just because the amount of change you see is a lot. And with ozone, you don't really see seasonal changes in the amount of ozone in the atmosphere. Whereas with water, you know, the amount of water vapor that we see in an exoplanet could fluctuate a decent amount just from weather variations.
Yeah.
And so with the water features, which are a potential indicator of volcanism, it's just a little more uncertain, just because, you know, are we seeing changes in the amount of water because of volcanism, or are we seeing changes in the amount of water just from some natural weather pattern? And with ozone, those weather patterns really don't happen. So I feel like it's more of a solid indicator than the water, but technically they both could be used.
Okay. I see we have questions coming from people. Before we're going to go through some of the questions, that's great. Ozone is a marker you mentioned that. However, let me point out that the absorption of ozone is between 0.2 and 0.3 micron, right? That's in the UV.
Yes.
And I can look everywhere around. I cannot find a telescope in space capable of detecting ozone absorption between 0.3 and 0.4 micron. So
right.
What do you have? What solution do you have to propose for that?
Very, very well worded question there. So in the paper, we modeled a hypothetical LIVOIR telescope. And so for those that don't know, LIVOIR, for anyone from France, I'm sorry if I'm not pronouncing that with the correct accent. But LIVOIR was a telescope that was planned to be built through some of the astrodecadals. And, you know, people in science are really bad with acronyms. And so LIVOIR literally just stands for Large Ultraviolet Optical Infrared. And so it is named that because it would be able to see in all of those wavelengths. But LaVoir ended up being canceled in replacement of a different telescope called the Habitable Worlds Observatory. And so it'll be something similar to James Webb, I believe, on a larger scale. So it'll be a bigger telescope where we will send it up to space and we will use it as a tool to look at exoplanets. And I'm sure, as is the case with James Webb, other things such as galaxies and star formation, things like that. And this is pretty far down the road with having this capability. I mean, I would assume that since it's still, I don't think anything is really in production with this new telescope. It's still just in talks. So it'll likely be at least a decade or two until we actually get something with this capability. But, you know, we're trying to just get an idea of, you know, what wavelengths would be useful on an instrument like that. And so that's why work like what I do and what other people in our field do is important, just to help show the engineers who will build stuff that we will use, you know, what is important to us and what might be important to exoplanet science.
Yeah. Yeah, that's very important, as you pointed out, that astronomers or scientists generally have an idea. They run models, they define a kind of requirement for the future generation of space telescope. And that's what you're doing. I mean, you're a fifth-year graduate student at UC Riverside.
Correct.
So if they launch this telescope, the Habitable World Observatory, in 20 years, you will probably be part of those astronomers that could use this project. I mean, yeah. I do remember when they were designing JWST in the 90s. Okay, and it looks like super far away. I'm seriously, like I say, oh, we never see this thing. Well, now I've seen it fly. I've not seen the launch, but I've seen that it's been in launch and open and get data. So do not despair. It looks far away, but you will see.
I'll try and be patient. Yeah.
In the meantime, you should continue to do models like that and get some great ideas. So we basically get more requirement for those future space telescopes. One question: you did that in reflection spectra. Do you think it's going to be possible to do the same kind of study in transmission?
Good question. And so for those that don't know, James Webb, what is currently observing exoplanets right now, is capable of transmission and emission spectroscopy. And so transmission spectroscopy is basically when an exoplanet will pass in front of its host star or in between us and its host star, and light from the star will be absorbed in the exoplanet's atmosphere, and we can detect that light being absorbed, basically. The problem, though, is that this method is only sensitive towards planets with smaller and cooler stars. And so, like, for example, the TRAPPIST-1 system, those planets orbit a M dwarf, which I believe is about like 20% the size of our sun. It's very, very small and much cooler. Those are the kind of planets that we're limited to with the transmission spectrum method. Whereas if we were to try and observe a Earth-like planet around a sun-like star with that method, the star would be way bigger than the planet and way brighter. It'd be a lot more light than what we see with the smaller stars. So basically the star would drown out the planet. But with direct imaging and hopefully the use of what we call a coronagraph, which I mentioned before, just blocks the light from the star, we'll be able to see an Earth-like planet around the sun-like star. So direct imaging would be needed, really, to observe an exact Earth analog.
Okay, good. We're going to take some questions. So we don't have much time. So what we're going to do is that you give us the shortest answer as possible.
Sure.
First question. Oh, I had it and I lost it. From BJB, what will be the source of this volcanic activity on those exoplanets? That's not the exact question, but I'm rephrasing.
Yeah. We would assume it would be through tectonic activity as well, and so that's why detecting volcanism would be really important, because it would help us understand that there might be tectonic plates or tectonic activity on an exoplanet.
Okay. Hendrik Hurst has a very interesting questions related to that. So what atmospheric observation will be diagnostic of the volcanism? If the exoplanet didn't have an oxygen atmosphere for ozone depletion, but had an atmosphere similar to Venus, so mainly CO2?
Great question. So since ozone was the thing that was preventing us from seeing the sulfur dioxide, it is likely that with a exovenus, we would actually be able to see that there is sulfur dioxide happening or in the atmosphere. It's a little more complicated than that, just because with Venus, the sulfur dioxide can last a long time in the atmosphere compared to with Earth. So it would be hard to tell whether we see sulfur dioxide because of present ongoing volcanism or it's a remnant from volcanism that occurred in the past. Great question.
Thank you. A question from Samantha Shiobara. Is it pretty much accepted as a scientific fact that all planets have tectonic plates or tectonic activity? Are there any other models of planet surfaces?
That's a great question. I think it's with the headlines that media puts out for some of these exoplanet discoveries, it's kind of lost that we really know very, very, very little about these exoplanets. A lot of this stuff is just us making assumptions and modeling those planets based on those assumptions. But we know very, very little concrete things about these. So we don't know for sure if other planets have, or exoplanets have tectonic plates. And it makes it even weirder because in the solar system, the Earth is the only one that has active tectonic plates. So we don't know if, we like to think Venus is like the weird one that ended up turning into a hellscape, but maybe in reality, Earth is the weird one, and tectonic plates are weird and not common, and having a habitable planet is weird and not common. So that's what we're trying to do is determine, what things with planets are weird and what things are normal.
That's a sad, a sad statement, because if Earth is a weirdo of the solar system, it will imply that life, as we know it, may be very rare.
Right.
Okay? That's the problem. But we're gonna go back to that in the future. Another question related to that from Velislava Lieva: what if an exoplanet has a different magma chemistry? I mean, we're talking of here. You simulated a volcanic activity that we can see on Earth with ejection of SO2 and so on. What if this exoplanet is very different in terms of volcanic activity?
That's a great question, and that sounds like a great idea for a follow-up paper. I mean, it's hard because we're focusing on one kind of eruption, and we're interested in exploring other things, but there's only so much you can do in one project. And for example, the eruption that occurred, the underwater eruption that occurred a couple years ago, that one actually pumped a mostly water into the atmosphere. And so we wanted to look into things like that, where the main output is water instead of sulfur dioxide. I mean, there still was some sulfur dioxide, but a lot more water than a normal eruption. And I guess in general, we're kind of just working with what we know. It could be possible that, there are eruptions that the main output isn't sulfur dioxide. It's something that we don't see here on Earth. But with the models we have, they're Earth-based models, and you could theorize kind of anything when it comes to exoplanets. And so we kind of just try and stick to what we know and work from there. But it's definitely a possibility that they don't have the same volcanic output as Earth.
Yeah, I would say that you have an infinite amount of possibilities, right? And as a scientist, what we try to do generally is to start by the most obvious one first. So that's why you basically simulated volcanic activity which are close to us that we
Mhm.
can see. You mentioned that this eruption that I forgot the name nearby
Yeah.
Tonga has
Mhm.
ejected a lot of water. So now you may go back to this and try to simulate that in the future.
Yeah.
But over time, we're going to go into more details about exoplanets. There will be more modelings about the interior of exoplanets and so on. And
Yeah.
some people will come out with some weird volcanic activity with different type of chemistry.
Mhm.
And people like you will work on simulating this. In fact, you have a job for the next 20 years until the launch of the Habitable Worlds Observatory.
Yeah, hopefully.
Congratulations.
Thank you.
Well, that's a good transition because we need to wrap up for the final question I have for you. So you're a fifth year grad student. I'm assuming you are getting ready to become a doctor and be asked in the airplane to save the life of people. But more seriously, what's your next step?
Yeah, hopefully that situation doesn't come because yeah, I mean, I'm planning on graduating sometime in the next 6 months. Hopefully, I definitely have started writing my thesis, and after that, the current plan will be to do a postdoc here at UCR. Just because kind of the way it works in the science community, or at least from what I understand, is you graduate with your doctorate, but there's still more work to do before you can really take on a full-time position. So I want to take a doctorate here at UCR, just because my mentor Stephen Kane is amazing, and I would really want to keep working with him. And then from there, after my doctorate, the current goal would be to get a research scientist position at NASA Goddard, just because the people there are amazing and their research interests fit really well with mine. But things don't always go as planned. So if that doesn't work out, I'm sure there'll be other options. But
It
that's
is
what I'm
good to
thinking
have a
for now.
plan.
Yep,
Always good to have a plan, to have
I
a
agree.
goal, a direction. It's a journey, right? That you don't know where the travel
Yep, it
will
definitely has
bring
been so far. Yeah.
you. All right. Thank you very much, Colby, for taking the time to talk to us about your recent paper on the study of volcanic activity on terrestrial exoplanets. It was a pleasure to have you at this SETI Live, and good luck with the rest of your career and your thesis first. And I hope we're going to have the opportunity to talk to each other again in the future.
Sounds good. Thank you all for having me. And thank you everyone for listening.
Thank you to all our viewers. This was a SETI Live. The SETI Live is a program organized by the SETI Institute, a nonprofit organization. Thank you for watching. You can support this nonprofit organization by sharing this video, by going on our YouTube, writing comments, telling us what you think, asking questions. Colby and I will monitor this and take the time to answer to some of them as well. You can also join our social media. We are on all platforms that exist so far. You can also go visit our website, seti.org, and click on the button on the top right, donate, and then you can make a small donation that could be used to support this program, to invite Colby to come to the SETI Institute to work for a month with us, for instance, on the study of exoplanet and volcanic activity. Here an idea. Okay. Thank you again, and enjoy your day wherever you are on this planet. And see you next week. Next week we're gonna talk about the OSIRIS-REx mission, if I remember properly, with Beth Johnson, not with me, but it's equally the same. It's as good. See you. Look up. Enjoy the dark sky and enjoy space. Bye bye.